Hello, this is the Heretic again, and today we're going to go into one of the most important topics in my version of modern physics. And this will leverage what we mentioned last episode, where I was talking about we need to understand how a particle, let's say this proton, and how it changes the universe as it's still or it moves, and how to think of it. See, the greatest error that physicists made was considering this proton a point charge. Now, from our perspective, looking very far away with a piece of equipment, the point charge approximation works because it's a small item and it just looks like a charge. But from the perspective of the proton, please understand that the proton's surrounded by the most densely strong electric field known to mankind except for the electron. In other words, it has a strong positive charge that is so strong that this electron, moving freely, coming within 10 million radii of this proton, would cause it to be captured and turn into a helium atom. Now, that's not a point charge. That's not a point charge approximation. Now, thinking of it as a giant field instead of a charge doesn't seem like that much of a difference until you move the proton. Let me give you an example. Let's consider that this location, this piece of paper is noting a location in space and time. As the proton is approaching, even now its large positive electric field is being seen by this point, and it will continue to rise until it hits a maximum. That maximum is just as the proton's passing, because it's closest to that point. Now, as it leaves, that point, one would think, should still stay charged. Nothing has reduced the charge, no action. But in actuality, as we all know, it goes back down. Now, what causes it to go back down? Well, as that particle moves past, a moving electric field induces, according to Faraday's law, a magnetic flux to occur. So now that magnetic flux is passing by, and that magnetic flux takes and reduces the charge at that location back down to zero. But that magnetic flux is also moving. And as that magnetic flux is moving, at the same speed as the proton was moving, it overshoots and causes that charge to drop below where the original proton charge was. In fact, below zero. Significantly below zero. Now, then that anti-charge is moving by, and as that anti-charge is moving by, it also is created a magnetic flux that is opposite into the previous magnetic flux. And that magnetic flux then restores back to a positive charge as it moves. and that positive charge goes back up. Now, I haven't talked about the magnitude of any of these items. And you'll find that the magnitude of each subsequent item is less than the previous item. And it eventually, like your standard wave will, or a water wave, will get to, at this point, get back to it's either zero or insignificant as far as we're concerned. Now, so at this point, it eventually gets restored. But there's a time delay, and during that time delay, several things are happening. And in fact, several magnetic fluxes and electric fields are generated that go through this single point. It's actually a very busy point in space until the proton moves far beyond it. Now, I said there's a difference in amplitude, and we will not get to the exact calculation for that till much later. But what I can say about the difference is that it's all dependent on one variable, the velocity of the proton. So that if the proton's moving slow, the disturbance is less and it bounces quickly. If the proton's fast, the disturbance takes a long time to end. Now, looking at a point in space, that's all well and good, but it's much more interesting when you look at it from the perspective of the proton. See, as the proton is moving, its electric field is moving. The electric field, as we said, creates a magnetic flux of opposite proportion. Again, Faraday's law. That magnetic flux is also moving because its source is moving. And it's generating, through Ampere's law, a charge. And that charge, because the magnetic flux was an opposite, is opposite to the original. And then the opposite charge, because it's going to be moving as well, creates a smaller magnetic flux that is antithesis to the first magnetic flux, which then generates a positive charge, much less than the original positive charge, and the process continues. Now, that whole process creates a enveloping cloak of varying charges and fluxes. And it, if we were to look at it, looks more like a comet's tail to the original particle.
So here we start with our proton in blue in the center. And outside the proton is the large orange positive electric field generated by that proton. And this is why I'm advocating not treating the proton as a point source, but instead as an electric field. This becomes more evident as we move it, because once we move it, we start to apply Maxwell's equations. First, Faraday's law, and later Ampere's law, to create the actual effect on fields and fluxes that we'll see. So here we start. We have our positively charged proton, and it's moving. That movement induces a negative magnetic flux. Again, Faraday's law. That moving flux induces, through Ampere's law, a moving charge. Please note that charge is smaller and, more importantly, opposite than the original charge. But that charge is, because its source is moving, is also moving. And that would induce a positive magnetic flux. And as you note, these items in the line of motion are appearing slightly behind the previous flux or field. The reason for that is they don't start to form until after halfway through its motion, which is what creates the tail-like effect. So this moving positive magnetic flux creates a positively charged field, electric field, just like the original field, but again, much smaller. And this continues with another flux, another opposite electric field, and a opposite flux. And if you notice, each individual item is smaller and its length is drawn out. The length and the intensity of each component is dependent specifically on the velocity at which the particle's moving. Now, we can also use this same methodology to deal with the electron, which in this case would have a minus charge, a positive field, again going through the steps just as before, but just opposite in each charge or flux from what the proton had.
That comet's tail of field, flux, field, flux, field, flux gives a very dynamic change to the behaviors of this particle, and more importantly, other particles as they interact with it. And if you do not have those fields and fluxes in that description of how that particle is going to interact, you're going to miss all the key things that it does. In fact, I'm not going to be able to get to the details here because they're long and distinguished. But one of the first things it does is, if you change the motion of this proton, its energy changes and a photon is released. Well, that photon is generated from that cone, enveloping cone, changing. If we move it faster, we get relativistic physics effects that come again from changes due to that cone. When we move an electron towards a proton, the thing that keeps this electron from striking this proton is applying those electromagnetic enveloping forces. And then what we're going to go into on the next lecture is what happens when we take a stream of these particles and we move them through a narrow slit. See, we're going to show that how this particle can act as a particle or as a wave, but the mechanism that causes it is there all the time. Wave-particle duality, I know, causes many people questions and mysteries, and most physicists I talk to say, well, wave-particle duality is why we have to have quantum mechanics. No, getting what happens with this particle as it moves is why physicists have gotten wave-particle duality wrong the entire time they talk about it. Not one physicist knows what is happening. They're guessing, and they're getting it wrong. But we'll fix that on our next lecture. Thank you very much for your time.